Today, we're solving differential equations in Python. This isn't necessarily an obvious or easy thing to do, and there's a lot of subtle steps you need to take to prepare your problem to feed it into Python properly, and that's what we're looking at today. We'll be looking at first-order differential equations, coupled first-order differential equations, how to prepare second-order and higher-order differential equations to pass into the SciPy functions that you use, and even a few precautions you need to take as well when you're dealing with complicated or chaotic differential equations. As always, if you enjoy, like and subscribe, join the Discord server. There's a link in the description below to that, and enjoy. So most of the ODE solving in Python is done with SciPy, and you'll see that I have two important functions here for solving differential equations. So other than that, we're just going to be importing NumPy and matplotlib. So we'll start with first order ODEs because I think these establish a basis of what solving everything else is going to be like. So I've chosen an ODE here. This is air friction when you're falling. I've covered it in other videos. Be sure to check those out. And so you have a dv dt minus alpha v squared, this is just some constant, and beta is a constant, is equal to 0. This is a differential equation with an initial condition. The velocity at time 0 is equal to 0, so you're just standing still. Now, if you want to solve an ODE in Python, you want to make sure that you package everything in the correct form. You can use those functions, and that's one thing, but you also want to package things properly. And as you get more and more into coding, you realize that everything is about packaging stuff properly. So we want to write our ODE in the form dv dt is equal to some function of t and v. Of course, a differential equation can depend on time itself. It doesn't in this case, and it can also depend on that quantity that you're actually taking the derivative of. So thinking about it in terms of English, derivative of v equals something that depends on v in time. That's what a differential equation really is in its essence. So this equation is really simple. We just move this over to the right-hand side. We get dv dt is equal to alpha v squared minus beta. This that you see here is that function f of t v. So we've written it in this form. So we're starting to put our package together that we can feed into SciPy. And like I said, there's no dependence on time in this example. So what we need to do is we need to write this in a Python form. And for that, we need functions. And so our function here, we define a function, dv dt, right? That's what you see here. It's a function that we call dv dt, and it depends on t and v. And I always write it in this form because it helps to sort of keep things organized like this. So, before we deal with any ODE solvers or anything, we're just writing a function. This is what the derivative is equal to. It depends on time and v. Time comes first. And we return, okay, well here alpha is equal to 3 and beta is equal to 5. So this is our differential equation. It's written like this in a Python functional form that we can eventually feed to a solver. And I have the initial condition here, v of time equals 0 is equal to 0. So now that it's packaged in this form, we can actually feed it into some of the SciPy modules that will iterate through different algorithms. These are very complex and they're sort of beyond the scope of this video, but there's lots of different algorithms they use, and those are dealt with by the solvers, and I'm sort of treating them like a black box in this video. And so there's two main functions that SciPy offers. There's ODE int. This is pretty classic, and it uses a particular solver called, I think this is L soda. It might be an I or an L, I don't remember. And it's from a Fortran library, ODE pack. So it's a particular solver when you use ODE int. Alternatively, there's solve IVP. This is far more customizable. There's a bunch of different solvers you can use, and it's actually a parameter to the solver. But when you use these two functions, you sort of pass them in the same things. There's a little bit of differences, and they spit out something that's a little bit different, so we have to get used to each. So here's my differential equation here. And so here I say, okay, I want to solve for a number of times. I'm going to solve for 100 times between 0 and 1, and I want to plot the solution between 0 and 1 second 100 times. That's what linspace does, of course. If I just copy and paste this, I believe I need to run all the code as well. So here's my time. These are the times at which I want to get the solution. You can see here, I want to find what v is. And so I'm going to solve it using both ODE solvers. I have ODE int here. It takes in this differential equation. Remember that this is the function that we defined above, dv dt. It takes in our initial condition. It takes it as just a scalar quantity, v naught. So y naught is the name of the parameter in this function. And our initial condition is v naught. So it calls it y naught, the argument in the function. T is the times we want to solve it over. So t equals t. That's just the times that we define here. And t first is equal to true. This is because ODE int and solve IVP are slightly different. You'll note that in this function, I have t comes first. Otherwise, ODE int actually expects v to come first. So I like to write it the same way because it'll work for solve IVP or ODE int. So I'm going to specify that t first is equal to true. This will give us one solution, and you'll see it returns an interesting object. Solve IVP, same thing. We give it the function dv dt. Then we have to give it a t span. So it needs to know how long am I solving this over? And it's solving between 0 and whatever the maximum value of this array is, which is 1. And y naught is equal to v naught. You'll note that I give it in an array form. This seems weird when you're solving one-dimensional ODEs, or just a system of one ODE. It makes more sense when you're solving systems of ODEs. And that's really what Python is for systems of coupled differential equations. And then the initial condition, of course, is just an array of many, many different things. And then the times to evaluate on, t eval, is t. That's this array here. So we can solve our ODE. And we can look at the two different solutions, and they return slightly different objects. So solution M1. Okay, it looks weird. It's a 2D array, and we have one thing each here. This is because if there were multiple quantities you were solving for, which we'll get to in a bit, if you have, multiple, maybe you're solving for y1, y2, y3, coupled things together, it would return like y1, then y2, then y3, and this corresponds to the first time, the second time, the third time. So because we're only solving for one quantity here, which is velocity, it only returns one thing, but if there were multiple things, this would be maybe 2 values, and this would be 2 values as well. And so if I want to extract a quantity quick, I can go transpose this array, right? And I take the first element, and that gives me my velocity. Now, obviously, there's nothing else, but if there were multiple things in this differential equation, or if it was coupled, or we had multiple differential equations together, then I can index to get the other things as well. So this is how I would get my velocity as a function of time, like this. We can also look at solution M2. This is a little bit different, how it returns from solve IVP. It actually returns a more complicated object where it says, okay, the solver successfully found the solution. It gives the number of iterations and a bunch of stuff. It says, okay, it's successful. And it gives this t, which are the times that it solves for. And it also gives t events, which is something else. And then it gives y. And y is the solution to the ODE. So if I want the solution, I have to go dot y. And it will give y. And like before, you'll see that it's a 2D array. And if there were multiple quantities, it would list them sort of, maybe this would be y1, then there'd be another thing after y2, y3, etc., etc. So they return slightly different objects. It's good to get used to both of them. And typically, I'd probably use solve IVP more often just because of the versatility of the solver. So here I'm extracting both the solutions. This is the v solution, so the velocity, using method 1. Method 1 is ODE int. And I just extract it like I did before. And solution M2, I extract the velocity here using exactly what I did before as well. Note that this is transpose. I transpose an array and I take the first element. And this is, of course, getting the solution in that weird solve IVP object. So I get both velocities and I can plot them. And you'll see that it indeed solves the differential equation the same way using both solvers. So this is an introduction to both solvers here. So what Python is really useful for is coupled first-order differential equations. And these are really the things that will show up all the time as you get further and further into research, going into topics, etc. And so this is an example of a coupled first-order differential equation. We have y1 and y2. These are two quantities that we want to solve for. And y1 prime is the derivative of y1, and y2 prime is the derivative of y2. But the derivative of y1 also depends on y2, and the derivative of y2 also depends on y1. Furthermore, there's this also dependence on x. So x is kind of like t in this example. And I purposefully chose to use x instead of t because often you'll be dealing with differential equations with variables that don't match, right? Like t here. The arguments say t here, but you have to think of t as an x. So it's getting used to. This is like the independent variable of the differential equation, the thing that you change and how everything else changes. So when you're solving coupled first-order ODEs, there's a strategy that I always use, and I would always recommend to do this because otherwise it gets sort of confusing. So there are two quantities that we want. We want y1 and y2, right? And there are two initial conditions for y1 and y2. So I define a vector capital S, and you'll see in all the videos that I do, I always use this notation of capital S. S is just a vector of everything that you want to solve for. It's very easy. So this is a vector that contains y1 and y2. Before we pass our differential equations to an ODE solver, we have to define a function, ds dx, and of course that's just the derivative of these two things. The function ds dx takes an s, so ds dx, which is a vector, depends on s, which is a vector, and x, right? So looking at it like this, so here's a vector s is equal to y1, y2. ds dx is a function, it's a vector function of x and s. So you can think of that as sort of analogous to this here. dv dt is a function of t and v. Now it's in a vector form because we have multiple variables. ds dx is equal to f of x and s. So this is like time, and s is the thing here. And you'll note that this can be written like this, right? So s is a vector with y1 and y2. So this is really a function that depends on x, y1, and y2. And of course, ds dx is just the derivative of y1 and y2. So y1 prime, y2 prime, which is equal to everything on the right-hand side here. So you'll note that I have above here, everything is contained down here like this in ds dx. So what I do in my Python function is I write a function, ds dx, and it takes an x and it takes an s, exactly like I have here. Now s is equal to y1, y2, so I extract those components from s, and it returns ds dx. So it returns whatever is here, the right-hand side of these differential equations. So all the information about the differential equations is contained here. So this is y1 prime here and y2 prime. So my ds dx is simple, like this. I have the initial conditions, y1 and y2, that I specify here. Of course, those can be numbers or whatever, that's fine. And I put it in initial condition s naught. So that's like the initial condition. So you can think of s as like a vector that contains all the information I want for the system. So I specify this. And we can solve this ODE. So I want to solve for a bunch of values between x is 0 and 1. And I'm going to use ODE int here. So I pass my ds dx function, exactly sort of the same like above. My initial condition, y naught, this is the argument name in the function. And I pass an s naught, which is a vector here. T, which are the times I want to solve for. Remember, it's not times here. This is equal to x, which are the x's that I want to solve over. I'm also using t first is equal to true. So I can solve this. And I can look at my solution, and you'll see what I mean. So these two values correspond to the first time. These two values correspond to the second time, the third time, the fourth time, well, x here, because x is an array. So this is the first time, the second time, the third time, the fourth time. Everything is discrete because you're on a computer, of course. So this is the first time, the second time, the third time, the fourth time, the fifth time. This is y1, y2 at the first time, or first x. Y1, y2 at the second x. Y1, y2 at the third x. So it's just you got to think of it sort of like in this way. If I want to extract like a column, of course, what I would do is I would transpose this and take the 0th component. That will give me y1. The next component would give me y2. So very simple, right? That's what I do here. I get y1 and y2 from my solution like this. And I can plot them. And so what I've done is I've solved my differential equation. And this is what the solution for y1 and y2 look like. So you might be thinking, everything we've done so far is for first order differential equations. What if I want to do higher order differential equations, like second order, third order, fourth order, or anything like that? Well, you'll see that any higher order differential equation can be converted into a system of first order differential equations. So Python doesn't have functions to directly solve second order ODEs. You need to take your second order differential equation, convert it into two first order differential equations. If you had a third order differential equation, that would be 3 first order. Or a fourth order differential equation would be 3 first order differential equations. And it keeps going sort of up like that. And I'll show you what you mean. So any second order ODE can be converted into 2 first order ODEs. And I'll show you how to do that here. So consider the differential equation x dot dot is equal to minus x dot squared plus sine x. This is a function of time, for example. So derivative of a dot means with respect to time. So I want to convert this into 2 first order ODEs so I can solve them like I did in the example above with 2 first order equations. So what I do is I take x, this is what I want to solve for, and I define x dot is equal to v, right? So v is a new variable here. This is a trick. And you get used to this trick over time. The first time you see it, it might be a little confusing. So v is our new variable. And x dot equals v is a differential equation, right? It's weird. I've defined a new thing, but I'm saying the derivative of x dot, it depends on v. So, okay, it's just a definition, but it is a differential equation. And the other differential equation is v dot is equal to minus x dot squared plus sine x. And x dot, of course, is just v, so this is minus v squared plus sine x. So we get two equations here just by introducing this definition. This becomes one of our differential equations. And our second differential equation, which is with v dot is equal to minus v squared plus sine x. So we're solving for both v and x. And so there are two coupled first order equations. So like before, I defined this ds dx, where of course s contains everything we want to solve for. So s is a vector of x and v, and it returns the derivatives here. I specify an initial condition for x and v, and s naught, the initial condition vector. And I can solve it like I did before. So everything is the same, and I get my solution here. So the important thing about this part is you have a higher order differential equation. You convert it into two first order differential equations using this trick here. Then you can package everything properly to put it into a Python solver. To really show off this here, and especially for higher order differential equations, I'll give an example that sort of summarizes everything so far. So here I have two coupled third order equations with x1 and x2. So I have a triple dot here. It's like a third derivative. And of course, these functions are a little bit weird. So x2 dot 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 and x1 dot dot dot. And I need to convert this into many first order equations. So for that, I need to do a bunch of definitions. I'll define four new variables here. v1 is x dot, v2 is x2 dot, a1 is x1 dot dot, and a2 is x2 dot dot. You'll note that this here, which is dot dot dot, I need to define new variables up to the dot before that. So if I have x2, like the third derivative, I'll need to define a new variable that's the second derivative. If this was like 5 dots, I would need to define all the way up to a new variable that's like 4 dots. So it's one less than the number of dots here. That's how I'm defining the variable, and then everything leading up to that as well. So I defined four new things here, and these are four differential equations like before. These are simple. I'm just introducing new variables, but they signify first order differential equations. Finally, a1 and a2, which are the dot before the one that comes here. If I take a1 dot, that's x1 dot dot dot, right? That's why I define one less than the one here, because then I can take the derivative of this one and I get the quantity here, and then it's just everything on this side. So a1 dot is equal to x1 dot dot dot, which is this here, and a2 dot is x2 dot dot dot, which is this here. And then I just plug in everything from up here. So a2 dot is equal to this. It's just a1 cubed, of course. a1 is x1 dot dot. So a1 cubed plus v2, that's x2 dot, plus x1 plus sine t. And these make up our final two differential equations. So we have 6 coupled first order differential equations here. We've turned 2 coupled third order equations here into 6 coupled first order differential equations. I encourage you to think about this and go through it really slowly, because this is essential for all differential equation solving in Python. So these are our 6 equations, and now I define S. So S is everything we want to solve for. We want to solve for x1 and x2, but we also have these new variables that we defined, v1, v2, and a1 and a2. So S is x1, v1, a1, x2, v2, a2. These are all 6 things that we want to solve for. Then ds dt is just, of course, the derivative for all these things. So x1 dot is equal to v1, that's by definition. v1 dot is a1, that's by definition. a1 dot is minus v2, 2v2 squared plus x2. That's just this equation here, essentially. Same thing with x2, v2, and a2 on this equation here. So my ds dt, like before, it's a function that takes in s and t. So I define ds dt, it takes in s and t. S is just all these quantities here, x1, v1, a1, x2, v2, a2, and it returns the derivatives, listed exactly like I have them in this column vector here. I specify all the initial conditions. Of course, you can change these, and my initial condition vector here, I run this, and like before, I just solve exactly the same. I pass the ds dt, my initial condition, the times I want to solve for, and making sure t first is true because t comes first in this function. So I can solve it, and I get a little solution like this. And this isn't any like significant differential equation or anything, but you see, more importantly, the process. So if you run into some math that you're doing, you get a complicated differential equation, you know exactly how to set it up in Python to solve it. I'll just give a final note here, and that final note is to be careful when you're solving ODEs. Not all solvers work for all ODEs. If you use these solvers like a black box, sometimes you'll get the wrong solution. So if you're doing research and you get an ODE, make sure you know everything about that differential equation. So in one of my videos, and there's a link here, and I'll put a link in the description, to 3-body planetary motion, you get a system of, I don't know how many of these are here, like 12 differential equations, 12 coupled first order equations. So these are a system of ODEs, but you can't just use an ODE solver out of the box. It will fail and it will diverge and it'll give some crazy solution that's not the right solution. It requires the DOPE 853 solver. You can use that in SciPy. And it also requires low values for rtol and atol. These are parameters for the solve IVP method. And there's a paper here about this system of differential equations. And so you always need to review the literature about your specific ODE, especially if it's a complicated one, before trying to solve in SciPy, because otherwise you might get a solution that's just chaotic. And so you need to play around with rtol and atol, like I said. So here's the SDT, and I'm going to put in all these equations here. So contains all these variables, and I define some things. This is just for the denominator here because it gets a little annoying to specify this every time. And here's the quantities. This is the SDT that it's returning. And I define my initial conditions. So there's 12 different things. There's 12 initial conditions. And I want to solve this. So here's my T, and here's solving it properly, right? And so if I solve it properly, and I look at y1, for example, which is the y position of the first mass, I get something like this. And this is the gravitational bodies sort of moving around each other. But what happens if I don't set these parameters here that are required? Well, okay, I can try solving it. And you'll note I get a completely different solution. And this is small perturbation since it's a chaotic system. If the solver does one thing slightly incorrectly, it can lead to a sort of chaotic and solution that doesn't really make any sense. And so we need to make sure we specify those rtol and atol. Same thing if I don't use this method, DOPE 853. If I just use a regular solver, it'll run into another sort of chaotic solution. So if you look at the pattern here, this is one bad solution. I plot it again and it does another bad solution. So make sure you have the right solver and review the literature for that, and also play with atol and rtol. And these are like the tolerance for the ODE solver. At each step, when I get new values for my solution, how careful do I need to be? Of course, the smaller those parameters are, the longer it takes to solve the ODE, but setting them small gives a better or more precise result for the ODE, and it's essential for chaotic differential equations as well. Anyways, I hope you enjoyed this video. There's plenty more content if you like this video. I have tons of videos in physics where I solve different physics problems that all involve complicated, coupled, ordinary differential equations. So look at my channel. Any of the Lagrangian mechanics, double pendulum problems, the 3-body gravitational problem, anything like that is all solving systems of coupled differential equations. Be sure to like, subscribe, join the Discord server, check out all the other videos, and I'll see you next time.